Hello and welcome to the Unit 10 Section 2 video on scatter plots and fitting functions. So now that we've compared all the different function types, now we have to be able to take a set of data that may not be perfectly configured for any particular data type, and we want to create a trend line that fits it the best that we can so that we can use the data to model something. Okay, so remember, we've talked about scatter plots before. It's been a while, it's been a few months, but a scatter plot shows two data sets as one set of ordered pairs. A trend line, or line of best fit, is a model for the data. And we're going to use Desmos to create a scatter plot and a trend line rather than doing it by hand. So let's talk about the line of best fit using Desmos. You're going to go to desmos.com and you're going to click on the graphing calculator. Then you're going to create a table by typing the word table into box 1. Now you're not going to see the word table like you see here. That's what you're going to type in, but at the moment that you put the EN on the end of table, you're going to get a table to just pop up, okay? Then you're going to input your data into the table. So you'll put all your X values in the left-hand column, you'll put your Y values in the right-hand column. And then you're going to click the Zoom Fit button to scale the graph to the data. So your Zoom Fit button is right here in the bottom left-hand corner. Then you're going to look at the data and determine which function type best models the data. Now, this is going to be a little bit of your call. Some of this is going to be more obvious than others. So there's going to be some data that could go with one or another type of modeling, okay? But some of it's going to be fairly obvious, and we're going to take a look at some examples here. Once you figure out which function type best models the data, then you're going to type in the box under the table of the model you selected. Okay, so you're in box 1 here. You'll go into the box below it and type in either the linear model, the quadratic, or the exponential. Now, keep in mind that the variables have to match what's in your column header. So you've got x1 and y1. So you need to put in y1 and x1 instead of just x and y, okay? You're also going to use a tilde symbol instead of an equals, okay, when you do this. Just a little bit of a note on typing into Desmos. If you're looking for a shortcut to doing a subscript in Desmos, you'll type in y_1, okay, and then the underscore is going to automatically put you into doing a subscript, okay? So it depends on what the data looks like as to which of these three you're going to use. So let's take a look at an example. The following data represent approximate heights for a ball thrown by a shot putter as it travels X meters horizontally. So what you're going to do, and I'm going to do this in class, and I encourage you to do this for yourself in Desmos following the instructions that I just gave you. But you're going to take all that data and you're going to put it into Desmos, and then you're going to see what kind of model best fits the data. So let's go ahead and do this one. So I'm going to pull up Desmos first, and then I'm going to go ahead and put all of this data into a table. Okay, so here is my data plotted in Desmos. I created my table, put all my data in, and then I clicked on the Zoom Fit, and here is what my data looks like. So now you got to determine, does this look linear, quadratic, or exponential? And given that it kind of follows a parabolic shape or a parabola shape, it looks kind of like it's a quadratic. So we're going to go into box 2 here, and we're going to model it as a quadratic. So to do that, we are going to do y_1, our tilde symbol, and then we're going to put in parentheses x_1 minus h, and then use the caret symbol to do our square, and then plus k. All right. Now we have a parabola, and we're going to try to make sure that this models to this. So now it doesn't look like it's modeling correctly. So this is an indication that we have something typed in wrong or that we've left something out. Okay, so let's look back at this again. We've got our H, we've got our K. What are we missing here? We're missing our A. So let's put that back in the front. Now this looks much better. Okay, so here is our trend line for our data. Okay, this is the parabola that most closely fits the data that we have. Okay, and we have in our parameters list a value for A, H, and K. So we can plug those values in, and that's going to give us the equation of our trend line. So let's go back to the notes. What model would best fit this data? Well, we've already said that this is a quadratic. In B, write a function to represent the data. Round to the nearest hundredths place as if needed. Okay, so we have this as our trend line, and there's our A, H, and K. So we're going to round each of these to nearest hundredth, which is 2 decimal places. And we are going to have this as our function. Now that we have this as our function, we can use this to estimate what the height of the ball would be if we traveled 80 meters for C. So you're going to plug in 80 into that function we just created, and that's going to give you 13.961 meters. And what would an accurate prediction for the distance traveled be? Well, we can also find that out by either plugging things into our function, or you can go back to your graph and we can see by just clicking over this. You may have to zoom in, see what the intercept is, 95.675. So we're going to make that our distance traveled. So once you have it in Desmos, you can most certainly use the graph and what Desmos is giving out to determine these things. You could also do that for the 80 meters. You could go back to this graph and you could go to 80 meters, which is here. Okay, and we can see what the value is at 80 meters, which is 13.961, which is what we got in the problem. Okay, so finding the trend line gives us all sorts of information that we can use. Let's try another example. 10 students from Ms. Jones' class reported the number of hours that they slept the night before their test. Their corresponding test scores are reported below. So first of all, we want to find out what model would best fit this data. So we're going to need to, just like in the previous one, start by plotting this data in Desmos. Okay, so here's my data that's plotted in Desmos. And I did the zoom fit so I could see all my data in the window here. And so now we need to figure out what kind of function best fits this. Well, I don't think quadratic's really going to do here. And I'm not quite sure exponential is really the way to go. You could almost say it here, but that's going to be a little bit of a stretch. So I think linear is probably going to be the most appropriate way to model this. So we're going to go with linear. All right, so now we're going to write a function to represent the data and round to the nearest hundredths place if needed. So we're going to go back to Desmos. We're going to go into box 2, and we're going to model this by doing y1 tilde, and then if you want to write it as mx1 plus b, you can do it that way because you're used to mx plus b as your form. And so now we have our slope here in the m and our b here in the y-intercept. So we're going to round these, and we're going to create our equation off of that. All right, what would you predict a student who slept 10 hours will receive on the test? Well, you can either take 10 and put it in for x and get your value, or if you want to go back, you can go to 10 on your line of best fit. So we may have to drag this over just a little bit. We can go to 10 on our line of best fit and see the corresponding value. So we're looking at about a 99.408. So we're going to say a 99. We'll round that down to 99%. Then for D, what would you predict a student who slept 3 hours will receive on the test? Again, you can put 3 into your function, or you can simply go back to the graph, and we're going to go to 3 hours on our graph. And it looks like 54.7. We're going to round that to a 55. All right. And then if a student received a 45, what would an accurate prediction about the number of hours slept before the test? So here you could plug in 45 for your y, or again, go back to our graph, and we're looking for the y value that is 45. And so here we are, about 45 here. So we're looking at about an hour, 0.47, so we're going to round that to 1.47. So the trend line gives us an idea of, all right, how many hours of sleep do you need to get a better grade on a test? If everything else was kept the same, the amount that you study and all of that stays the same, what kind of impact does sleeping have on your test score? So the moral of the story here in this problem is you need to get good sleep on a night before a test. All right, let's go ahead and revisit a topic that we've already covered several units ago, and that is correlation. Remember, correlation describes a relationship between two data sets. A graph may show a correlation between data. The correlation can help you analyze trends and make predictions. There are 3 types of correlations between data. You have positive correlation, where both sets of the data values increase. So as your x increases, your y is also increasing. Negative correlation is when one set of data values increases and the other set decreases. So here our x is going up and our y is coming down. Okay, and then no correlation is when we can't get a read on as to whether or not there's a positive or negative correlation. Everything's just kind of spread out, so we can't tell if we would have positive or negative here. So in example 3, let's determine the type of correlation, whether it's positive, negative, or no correlation. So for A here, well, it's kind of hard to get a read. Here it looks like it's going up, but here it looks like it's going down, and we can't really make a good judgment call as to which one we should go with. So this one would be no correlation. For B, everything is generally heading in an upward direction, so that's positive. And in C, everything's generally heading in a downward direction, which is negative. We can also determine the correlation given a real-world scenario. So the height of a candle, the amount of time it stays lit. Well, we know that the height of a candle is going to go down as time goes up. So since one's going down as the other goes up, that's going to give you a negative correlation. For B, the amount of rainfall on Fridays. Well, is there a correlation there? I mean, some Fridays it rains, some Fridays it doesn't. Sometimes it will rain 3 Fridays in a row. Sometimes it will rain just one Friday and then be dry the other 3 or 4. So there's no correlation here. In C, the price of pizza and the number of toppings added. Usually when you add toppings to a pizza, the price is going to go up. So as the number of toppings go up, the price goes up. So we have a positive correlation. So we can actually put a number to the correlation and call it the correlation coefficient. We've talked about this before, so this is a little bit of recap of something we've done. So the correlation coefficient is a measure of how well a correlation of data points can be modeled by a trend line. Okay, Correlation coefficients range from -1 to +1. The closer the correlation coefficient is to -1 or +1, the less scattered the points are and the stronger the relationship. So we have a strong negative correlation when we're close to -1. We have a strong positive correlation when we're close to +1. The closer the correlation coefficient is to 0, the more scattered the points are and the weaker the relationship. So we have here kind of a line here from -1 to +1. If you're close to -1 or if you're at -1, you have perfect negative correlation where the line with a negative slope fits best. Okay, if you had -1, every one of your points is going to fall on your trend line. Same with positive correlation, just in a positive slope. And then no correlation means that you have absolutely no pattern existing, and that would be indicated by a 0. All right, so now in these last few examples, we are going to talk a little bit about analyzing the data that we have and seeing if we can answer some questions about it. So in example 5, the table shows the total fat and the total amount of calories in various fast food items. So what model would best fit this data? So what we're going to have to do is go back to our method of putting all of our data into Desmos and seeing what comes out of it. All right, so here's our data in Desmos. I put all the data into the table, and I have plotted it out on our graph using the zoom fit so I can see all of my data. And this most certainly looks linear, right? It looks like we could put a line somewhere through this data. So I'm going to go ahead and model that, and then we'll get to answering the questions. So we've got y sub 1 tilde, and then mx plus b. So mx sub 1 plus b. And then here gives our slope value and our b value as well, which is our y-intercept. So that gives us our equation that we're looking for. So now, let's go back and answer some questions. What model would best fit the data? That would be linear. What is the value of r, the correlation coefficient, and what does it mean? So let's go back to Desmos, and let's pull up our r. Well, here it is right here. So our r value is 0.9746. So I'm going to put that here. And what does that mean? Well, that means that we have a strong positive correlation because that number is very close to 1. So it means how closely the trend line fits, and it also means that we have a strong positive correlation. Describe the strength of the relationship between the total fat and the total amount of calories. So we just kind of talked about that, strong correlation. Write a function to represent the relationship between the total fat and the total amount of calories. So to write that function, you're going to take your m value and you're going to plug that into m here. You're going to take your y-intercept, plug it in for b, and you're going to write out your equation. So there it is. Okay, a couple more questions. What is the predicted number of calories on a hot dog that has 18 grams of total fat? You can either use your equation by putting 18 into x, or you can go back to your graph in Desmos and find 18 on your trend line. So let's see, 18 on my trend line is going to be here. So we're looking at about 405 and some change. So we're looking at about 420 calories here. Actually, let's go back here. If we're looking at 18 grams of fat, yeah, it looks like it should be more of 405. That's a typo. So it should be 405, not 420. Approximately, what is the total fat in grams of a sandwich that has 350 total calories? So you can put that in for y and find what your x is, or, again, go back to your graph, find 350 calories on your graph, which would be your y value, and it looks like you're going to be somewhere in the 13.4 range. And again, it looks like I have a typo here. It should be 13.4, not 11.185. Okay. Now let's do a little bit of comparing of function types. Okay. Two people, Adam and Bianca, are competing to see who can save the most money in 1 month. Use the table and graph below to answer the following questions. So in Adam's savings, we have a graph, and Bianca's savings, we have a table of information. So if we want to make some comparisons, let's write the equation for Adam's graph and Bianca's table. So for Adam's graph, we know that the slope is 3 over 1, which is 3, and we know that the y-intercept is 3. So that gives us, for Adam, y equals 3x plus 3. Now for Bianca, we can find the slope by doing y2 minus y1 over x2 minus x1, provided this is linear. And if you check this, I think you'll find that this is indeed linear. So we have the slope. How do you find the y-intercept? Well, we're going to backtrack this to 0, okay? Because we know what the slope is, and you know that you want number of days equals 0, you can solve that in your slope equation. And so you're going to end up with y equals 3x plus 2. So now, let's answer a couple of questions. Determine who will save the most money at the end of the month. Well, let's see here. At the end of the month, we are going to have how many days? Well, let's say 30 days. If you put in 30 for x here and 30 for x here, Adam is going to have $1 more than Bianca at the end of the month. So Adam will save more. How much money will each person have at the start? How much did each of them have at the start? Well, Adam, your y-intercept is 3, so Adam started with $3. Bianca, the y-intercept is 2, so Bianca started with $2. And since we are increasing linearly, and Adam and Bianca are both increasing at the same rate, Adam is always going to have $1 more than Bianca going day to day. So that's why Adam also has more money at the end of the month. All right, 2 small rockets were launched, and their paths are modeled by the graph in the equation here. So we have rocket A and the graph for it, rocket B and the equation for it. Which rocket reaches a higher maximum height? And what is that height? Well, we can find that easily for rocket A. Okay, we have the maximum height at around 255, but we have to use the equation to find what the maximum height is for rocket B. And to do that, we have to start by finding the axis of symmetry. We have to find the time we're at the max. So we do that using our A and B values out of our equation. And we find is that time equals 2. Now we have to take that time of 2 and plug it back into our original equation to find out what that height was. And the height for rocket B was 64. So rocket A is going to have a higher maximum height at 255 feet, which is read off the graph here. Which rocket hits the ground first? Well, we know that rocket A is going to hit the ground at 8 seconds. We know that rocket B took 2 seconds to get to its maximum height, so it's going to take another 2 seconds to get back to the ground, so it's going to hit the ground at 4 seconds. So rocket B is going to hit the ground first at 4 seconds. Which rocket is higher after 6 seconds? Well, we know it's going to be rocket A because rocket B has already hit the ground at 4 seconds. So we're going to look at our graph, and at 6 seconds, it looks like we're at about 190 feet. So this should say rocket A is going to be higher at 190 feet. So this is not rocket B, this is actually rocket A. All right, last example here. After graduation, you're offered 2 jobs. Cedar Grove Associates offered to start you at $30,000 with a 6% increase per year. Maple Grove Associates provided you with a table to represent your salary for the first 10 years as shown below. Use the information given to answer the following questions. What type of function does Cedar Grove model? And what type of function does Maple Grove model? So Cedar Grove, since we're increasing and we have a rate, which is our constant ratio, and a starting value, Cedar Grove is exponential and is modeled with this equation. Our starting value is 30,000. We're increasing at 6% a year, so you've got to keep the 100% of what you've already got, add another 6% to it, and that's what you get per year. For Maple Grove, let's look at the table. We start at 40,000, then we go to 41,200, so we added 1,200 here. And then to here, we added another 1,200, and then we add another 1,200, and that keeps on going on down the table. So we have a linear progression for Maple Grove, and that is modeled by taking 1,200 times the number of years you're with them and adding to your start, which is starting at 40,000 at year 1, but we have to start at year 0, okay? Year 0 is our y-intercept, so we're going to subtract 1,200 from 40,000 to model our value here. Because if you're starting at year 1, 1 times 1,200 gives you 1,200 plus 38,800 gives you the 40,000 that you start with. So that's how you model the linear one. After 5 years, at which job would you be making more money? Well, now we can just take the two models that we've created and just plug in 5 for x on our exponential model for Cedar Grove, and that gives us $40,146.77. And then the same for Maple Grove. We're going to plug in 5 for our x, and that gives us a value of $44,800. So after 5 years, you will be making more money at Maple Grove. Now, which company would be the better option to choose as a long-term career? So again, we are going to use these two models. And let's go all the way out to year 10 and just see what we get. So at Cedar Grove, you've got 10 years out, you'll be making $53,725.43. And really, we don't even have to use the equation. We can, but you can just read it off the table. You'll be making $50,800 at Maple Grove. So by the time you're 10 years out, you will have surpassed what you would be making at Maple Grove, and you'll continue to make more money at a faster rate because Cedar Grove would be a better long-term career choice since the salary would be more after 10 years and will continue to grow faster since this is an exponential function. So this kind of gives you an idea of how we can take some real-world scenarios and how we can take different function types and make some comparisons and see where you end up in a better position. And this does happen in the real world. Some companies will pay you a straight amount more each year, and some companies will give you a percentage raise. And that percentage raise is going to mean more year to year because as your salary is higher, that percent is a bigger amount because your salary is higher. Okay, so these are real world things, good things to learn about and know about. All right, that wraps up section 2 and unit 10.